I should say, first of all, one thing very positive about my teaching this thing on Zoom is that I have a bad cold at the moment. So, so at least you people are all protected from it. So that's the main positive side. So of course the downside there is that I may have to. So the data file we will get to in the course of today, and then this file is pretty much what we will analyze the different tabs in it for the rest of the 6 weeks. This is how I start my my teaching. And when times were good, I would sometimes go pick up my mother-in-law and bring her to town for dinner or something, or to spend the day. So I might drive to work to the medical center, and then she lives in Great. So and so I would, go to Google Maps and ask how long is it going to take me to get to Great Neck. And so Google Maps tells me at that time, some sort of rush hour, I think, an hour and a half. On a good day, it takes me like 35, 40 minutes. So would somebody like to tell me how Google Maps knew it was going to take me an hour and a half to get to Great Neck from the medical
center? So I would assume that they probably have like all these algorithms that are analyzing, the traffic pattern data, and at this time of day they can set, on a weekday, the probability of there being a traffic jam is this long, and then I think for any recent like accidents or something like that, there are like satellites that are, saying, okay, now there's an extra hold up here this day. That's my assumption. I don't know if it's correct.
Zach, I think that is way more than I knew, and I agree with everything Zach said. Zach, say I did this on Wednesday at 5 p.m. someday. Now, if I had asked the same question of Google Maps exactly a week later, even if there were no accidents on either day, it still would not give me the same answer.
You're saying 5 p.m., like the exact same day, 1 week later?
Right, 1 week later. So it's the same weekday.
Maybe certain people's traffic patterns change to avoid, they decide to go to a different way.
Right. So how does Google Maps know that?
I'm not too sure. I was just going out on a limb since.
No, Zach, you are, as I said, you're way ahead of where most people are. So would anyone else like to add something to what Zach said? I mean, Zach's account of the algorithm is very good. There is one key element there, Zach, which is that most people driving have Google Maps on their phone. And even if they are not looking at Google Maps on their phones while driving, their phones are communicating with some central thing of Google Maps. So when I ask Google Maps how long will it take, it actually knows how fast all the phones are moving on these roads. So the roads that I have to take, I lost my cursor. This is the road it wants me to take. It knows what how fast the traffic is moving. So that's where all these red and green and blue and so on. So they are actually arrived at not just from the algorithm, and you're right, it does take its history and stuff, but it actually knows what's happening. And anyway, I have spent way longer than I should have on this slide. But the point actually for me is that people don't need to know how Google Maps works to use it, to find out how to get there. So that's fine. And most of us don't know how it works, but we know how to use Google Maps. We know to launch it, put in our destination, and look at what it offers and go ahead. And that's what I want to do when I teach that. I'm not interested in teaching you theory at all, not at all. And so the goal is to be self-sufficient in running statistical analysis. And so the theory, I do very little. The goal, I want you to be able to tell when to use a t-test, when to use a chi-square test, when to do regression, and so on. But not any of the theory behind it. How is the t-statistic derived? How are confidence limits derived? I'm not interested. And these are my TAs for the moment, and Isabella, who has experience from before, she's helped me many, many times. And Nidhi Vinod and Karina Chan are the other two. While we're going through, if you have any question about what I'm saying, something's not clear, raise your hand or post a question in chat. But if you think the problem is just specific to you, like I'm showing that you do something and you'll get something and you don't see it on your computer. So then send a private chat, not to everyone, but a private chat to, say, Isabella or one of the other two. Maybe just to send to Isabella to start with. And then they will then do a private chat with you or possibly go into breakout rooms. We think the TA and you should be able to go into a empty breakout room, and then you can share screen, etc., and work out what the problem is. So this is the overall picture of what we're going to do. And we're going to start by doing 2x2 tables, and then we're going to switch to Excel and do whatever we can do in Excel, which is not much. We can do t-tests and we can do correlation. That's all you can do in Excel by way of statistical analysis. Data management, data manipulation, you can do in Excel a lot. But analysis, those two are pretty much it. And then we will do power analysis, which again does not require, because we have written a web page to do that. And then we'll switch to R. And all the major statistical analyses will be done in R. So yeah, I have to think about that. I hope I have it set up on course. So yeah, maybe this would not be a bad idea. And actually, there aren't so many of you. Maybe it's best just email me. So I would like you to try to install R over the course of next week. And then you should be able to just copy the console output and send it to me. And so then I can look at that and decide whether any help is needed. So that there are some little hiccups sometimes people have in initial installation of R. And so at some point in the third session, we will set aside time in class to make sure that everybody has their R and the various packages needed. Okay. And yeah, when you're all done and installed R, you'll get a message. Okay. And I have no interest in anybody learning to program in R. We developed some functions, and I'm going to teach you how to use them. And then over time, I'll show you. We have a crib sheet that will help you type, the right commands and so on. And I also have a web tool where you can go and pick various checkboxes, and then it will produce an R command that you need to copy and paste. Okay, enough with all that. So Uh, so a brief overview of the lecture topics, 2x2s, which I'm going to come back to. And as I mentioned, not much you can do in Excel. And then we'll do power analysis. And these are the major analyses topics in R. So we will do, ANOVA, repeated measures, multiple regression, and logistic regression, Kaplan-Meier, Cox model. So it's pretty much everything that I do in my own work. I do very little beyond this. So I think I'm happy teaching this. Okay. So good. So we're going to start with categorical analysis. And so first of all, people should be clear what is meant by categorical data. So categorical data are typically variables that take only two values, or maybe three values. So you can have an outcome, person lived or died. It can have an intervention, treatment or placebo. You can have a risk factor, somebody smokes or doesn't smoke. And so what we're going to start with today is looking for associations between two categorical data. That is, you have some risk factor, you have some outcome, they're both categorical, and we want to see what the association. And so the point that I want to stress is that we have a web page that does 2x2s, various types of 2x2s. And there are 5 types of studies that can lead to 2x2. So I'm interested in everybody becoming clear about that. And you can have an intervention study, you can have a case control study, you can have a complete cohort study, or you can have a matched cohort where you take people who are exposed to a risk factor and you find controls for them, and then you look at the outcome, or a more complicated thing, propensity matched, which I'll get to later. So there are 5 different types of studies, and they all end up with a 2x2 formulation, and you get a p-value. But the interpretation is very different for the different types of studies. It can be different. And so that's what I want to stress now. Throughout these lectures, we're going to be analyzing actual data. And so the 2x2s are no exception to that. So I'm first going to give you little summaries of reports in the literature of the different types of studies that I want to talk about. So intervention. So a few years ago, there was a study in West Africa that looked at the effect of providing antibiotics along with renourishment of severely malnourished children. And so the question was, will the antibiotics help with survival? A lot of these children die. And so what they found, they actually looked at 2 antibiotics, but we'll forget that. We'll just focus on 1 antibiotic in placebo. So they say in the placebo group, 7.4% died, only 4.1% died on ceftiofur. And they also say how many they studied. So this is what you end up with. You end up with a 2x2. So there were about 920 in each group, placebo and ceftiofur. 68 of the 920 died on placebo, and 38 of the 923 died on ceftiofur. So the question is this statistically significant? And what sorts of summary statistics can be produced from that? So we'll come back to this, to that story and actually do the analysis. But I want to go through the other 2x2 scenarios first. So a case control study. And so I believe this was done at Kaiser in California. So they were interested in seeing whether kids who had congenital heart disease were at higher risk for stroke during their childhood. Now, the one thing to be very clear about is that a case control study is appropriate when the outcome you're looking at is very rare. That's the main use for a case control study, in my opinion. So in this case, for instance, I'm sure they have millions of kids in their system, only a small number have stroke as children. And so it's very appropriate to do a case control study. So they say in the abstract, it's there are 2.5 million kids, and they had 412 cases. So there were 412 kids who had childhood stroke. And they got 1236 controls to match. So they say they matched age, facility matched stroke. So the first thing to note here is that a case control study does not have to have the same number of cases and controls. It is actually best if you can have more controls for every case. 2, 3, 5. Beyond 5, in my view, there is diminishing return. So maybe you don't gain much by having more controls than about 5 to a case. But in my view, up to about 5 to a case, you definitely increase the power of your study. That is, your study is more sensitive and can find smaller effects to be statistically significant. And so if you're designing a study and doing a case control study, it's always good to get not one control per case, but 3, 4, 5 controls per case. So in this case, they use 3 controls per case. So, and within those, they found congenital heart disease in 15 of the cases and 7 of the controls. So this is what their data look like. So you can see, again, this is a 2 by 2, but the cells that are filled are a little bit different. So here they start off with the total cases and controls and how many had the risk factor in the cases and in the controls. And you want to analyze these data to see significance. So a third story, this is a complete cohort. And so I've not at all, they were unfortunately, given all sorts of irrational, stupid fears about vaccines, which we came across this year as well. So this research effort was undertaken to study whether in fact the MMR vaccine increases autism risk. I mean, they concluded that it doesn't, obviously, but I'm just interested in a tiny preliminary aspect of the study. So they decided to look at children who had an older sibling, and those children whose older siblings had been diagnosed on the autism spectrum disorder. And so the thought was that those kids would be at a higher risk for autism themselves. So then the paper goes on to see what the effect of the vaccination was. But we're not going to look at that. So I'm just interested in seeing whether a child has an older sibling with ASD, is that child at higher risk for ASD themselves? So I don't want to go through all the things, but so this is what the data looks like. They had close to 100,000 kids in their cohort with older siblings. So of those 96,000 kids with older siblings, 1929 of the older siblings had ASD. And of the 96,000 kids with older siblings, about 1,000 of those kids themselves had ASD. And they say that 134 of these 1929 or 994, fall into this stuff. That is, of the kids with 1929 older siblings with ASD, 134 had ASD themselves. And so the question is this significant? Can we say that having an older sibling with ASD increases the risk of a child developing? Okay, so I'm sorry, there are so many examples here. We're going to go back to all of them and do the calculation. So this is what is called an exposure matched cohort study. And the exposure match cohort study is not unlike a case control study. It looks like a case control study, except that in a case control study, you start with cases. Like the example we saw, we started with kids that had childhood stroke. And then you found controls for them, and then you explored various risk factors. Here, the interest is in celiac disease as a risk factor, not as outcome, but as a risk factor. So they wanted to study whether celiac disease increases the risk of primary hyperparathyroidism. And so their cohort consists of lots of Swedes, but they had 17,000 with celiac disease. Now, if you remember, celiac disease here is a risk factor, not an outcome. And so for each of those celiac disease subjects, they found roughly five matched controls. So again, see the similarity to case control. This is again, you're finding controls to match, but you're finding controls to match for the exposure, not the outcome. So they got 5 controls for each celiac disease subject. And then they looked to see what the PHPT incidence was in the 2 groups. And this is what they got. So they had 17,000 celiac patients, subjects, and 85,000 controls. And in that, they got 68 of the celiac developed PHPT and 172 of the others developed. And they asked the question, is this significant? Does celiac disease increase the risk of your developing PHPT? So the one thing to note along the way is that all these studies have a 2x2 for the cells and totals. But you see that different studies, you end up filling the table starting at different points. So here, for instance, you're starting off with the row totals and the outcomes. So it's very similar to what happened in the intervention study. In the intervention study too, they would start with the row totals and count what the outcomes is. Whereas in a case control study, you start with the column total. How many cases you have, how many controls you have, and what were the outcomes. So there is a difference in the way you are constructing the 2x2 table. You're ending up with a 2x2 table, but in a case control study, you're starting with column totals, and in an intervention study or an exposure match study, you're starting with the row total. And this, I'm mentioning this because this influences how you can interpret your results in terms of odds ratios or relative risks or other summary statistics you may want to do. And in a complete cohort, you actually start with the grand total and then you divide it up in the various. Okay, so the final type of study that I want to mention is a propensity match cohort. And a propensity match cohort is sort of like exposure matched. So in the example we saw, they wanted to study celiac disease as a risk factor. So here you may be interested in, for instance, in this particular study, they were interested in freestanding children's hospitals like Columbia, how they compare with non-freestanding hospitals, say like what Weill Cornell has for pediatrics. So they wanted to compare freestanding and non-freestanding hospitals in terms of kids that went to an ICU, what the ICU outcomes were. So they start out with a huge number of patients, but they matched by propensity. I'll talk about propensity matching later. It's a little bit like matching for multiple potential confounders. Not a little bit like that's what you're doing. And I won't go through the procedure here. I'll talk about it some other time. So when they matched, the 500,000 got down to about 130,000, and they were able to get a 2x2 from that. They had 67,000 odd people in freestanding hospitals and about 67,000 odd patients in non-freestanding hospitals, and these were the outcomes. Now, this looks very much like an intervention study or an exposure match study, and in fact, it's analyzed in a very similar. Okay, so intervention, case control, or cohort, there are different types of studies, but they all end up with these 2x2. And it could be a risk factor and cases and controls, or it could be a treatment and positive and negative outcome and so on. But they all end up in 2x2. So I should say something up front. I'll try to remember when we get to the web page that we have. My convention in writing 2x2 is to have the cases or the negative outcomes as a second column, and the risk factor of interest or a treatment of interest be the second row. This is arbitrary. Different people set it up differently, but this is what you will find I'm doing. And so that goes with, that's what our web page expects you to have the data. I hope people understand what I'm saying. There is no, you could have cases and controls in the opposite order here. You could have the risk factor high and low in the opposite order here. The p-value is not going to change, but it's just that summary statistics change, and so we adopted this particular layout. So let's start with a simple table. Say you have 300 people, and you had 100 cases, and it's a case control study. 100 cases, 200 controls. And within those, of 300 total, you have 60 people who had a high level of the risk factor, and 240 who did not. And so this is what you want to study. So these numbers are called marginal. That is the column totals and the row totals. The numbers of cases and controls, the numbers of low and high levels of risk factor. So this is the margin. Now, just to be very clear, the marginals themselves do not indicate whether there's an association or not. Is that clear? Any question there? Right? Because this is just saying you have 300 people, 100 of them are cases, 60 of them have high level of risk factor, but says nothing about the association. Now, if there is no association whatsoever, then what you should have is that since cases are 1/3 of the total, if 1/3 of the high risk factor happen to be cases, so the 60 gets split as 40-20, then the 240 will get split as 160-80. So this is what you would expect if there is no association. Now, if, say, instead of 20 cases with a high risk factor, you have 30. 30 out of the 100 have a high level of risk factor. Then maybe there is an association. Okay. So the next thing is that you can, once you have the 30, you can readily calculate the other 3 steps. I hope that's clear. Right? Because because you have the total, you can subtract the 30 from the 60, 30 from the 100, and so on, and get the rest of the stuff. So now we can ask, is this statistically significant? And so one way that this is done is through calculating what is called the odds ratio. A lot of you may have come across odds ratio. It helps to have a good understanding of odds ratio. It helps to know, first of all, what the word odds means. So would somebody like to say what they understand by the word odd? Because then we'll go from odds to odds ratio.
Does it mean that the chances that if you have a high risk factor, you'll have a case?
Well, I think you've gone on to odds ratio. I first just want to understand what is meant by odds. So then we can talk about odds ratio. So for instance, if you're going to calculate odds at the low risk factor level and odds at the high risk factor level.
I was going to say like the likelihood of a certain outcome given a certain situation.
Okay. So what would the likelihood, the likelihood, would that be the same as the chance or probability, or do you mean something else by the word likelihood?
Yeah, I think for me it means the same as probability.
Okay. So in this case, like you have 240 people at low level of the risk factor and 80 of them were cases. So what would the odds of being a case be, you think?
80 out of 240.
Right. So this is what a lot of people think odds mean, but it doesn't. So any other guesses?
Comparing like the likelihood of being a case to the likelihood of being a control?
Excellent. Yeah, that's it. So that's what the odds are. So the odds are the chance of something happening divided by the chance of it not happening. That's the definition of odds. So it really goes back to horse racing in England and elsewhere, where if you went to a dog race, if you went to a race and you wanted to bet on an animal, you would put down, say, 5 pounds or 1 pound, and the bookie would put down, say, 3 pounds. What the bookie is saying is that your animal has 1/3 the chance of winning as losing. You have 1 pound and 3 pounds. So the 1 to 3 becomes the odds quoted by the bookie. Now, the chance of your animal winning is 1 out of 4. But the odds of your animal winning is 1 to 3. So that's sort of the origin of the term odds. And it turns out that in case control studies, the odds ratios are the natural thing to calculate, and they are the correct thing to calculate. And I'll talk about why that is in a minute. But the unfortunate thing is that over time, the word odds has come to be synonymous in common language with probability. And so that makes it a little bit harder when you have to learn odds ratios to be clear in your head. Like when you read a paper, medical paper, and they report odds ratios, and so you have to be clear what they're talking about. And I'll talk about how odds ratio is different from relative risk. It's not the same. Relative risk is you work with the chance, as Kathy said, of something happening, and some people call it rate ratio, and the ratio of that between high and low risk factor or intervention and placebo and so on. And those numbers you calculate are different for relative risk than odds ratio. Okay. So so you can say what is the odds ratio here where there was no association, and what's the odds ratio here where there is an And so I'm going to skip this. It's a reporter for the New York Times who's very, very good economics reporter. And just to show that he, in fact, makes this error in his writing, where he says odds were 14% or 9%. He's actually talking about probability, that the chance is 22%, 14%. If he actually wanted to talk about odds, he would have to calculate odds the way, as you mentioned, something happening over that not happening, so that a 22% chance becomes 0.28 odds, not 0.22, and so on. And then there was a Supreme Court decision that I noticed where, Stephen Breyer, for whom I have the greatest respect, said the odds are greater than 50-50. So, and this is an accurate statement. That's how you look at odds. So, Breyer didn't say odds are greater than 0.5. He said the odds are greater than 50-50, even. The odds are better than even. That means the probability is more than 0.5. And so that's, so Stephen Breyer was quite correct. And I have this video, which I won't show you, where before the 2018 midterms, a while ago, Schumer was hopeful that the Democrats would win a majority of the Senate, which they didn't. But so he says in the course of the interview, I think the odds are greater than half will take back the Senate. So he doesn't mean odds are greater than half. He thinks the chance is greater than half that will take back. But again, he's using odds as synonymous with chance or probability. Okay, so back to the table. So when you have no association, the odds are 80 to 160 or 0.5, 20 to 40 or 0.5, and the odds ratio is just divided by this, and it's 1. Now, if instead of 20 cases at the high risk factor, you have 30, now you have 70 to 170 odds of 0.4 and 30 to 30 odds of 1. And so now the odds ratio becomes 2.43. Is it clear how I'm calculating the odds ratio? Okay. Now, I could calculate risk. In a case control study, it would not be correct, but I just want to show how the numbers are different. So I'm sorry, I got the message from Isabella, and no, I think I'll stick with this table here. So this table doesn't show an association because each row you have the same ratio. That is, the control to case ratio is 2 to 1 here and it's 2 to 1. Or to put it differently, the number of cases as a fraction of the total is 1/3 overall, and it's 1/3 in the high risk factor and 1/3 in the low risk factor. So, so if you have 2 levels of your risk factor and the outcome is not different between the 2, the numbers are different. You have only 60 people with the high risk factor, and you have 240 with the low risk factor. So the numbers are different, but the ratios are the same. So you have 20 out of 60, 80 out of 240, or if you want to look at it as 40 to 20, 160 to 80. There's no association there. That's what we mean by no association. Whereas when the 20 becomes 30, these ratios are now different. You have 30 to 30 or 170 to 70. Or if you talk in terms of chances, 30 out of 60, 70 out of 240. So the two rows are different. So there is no association means really that there is no difference in terms of how things are distributed when you go from low to high risk factor, or when you go from control to case. This is the odds ratio. So what I wanted to do next was to show how if you compute risk or rate and you calculate the risk, relative risk or rate ratio, it's not going to come out to be the same. When you have no association, they both come out to be 1. The individual numbers are different. Here it is 0.5, 80 to 160, 20 to 40. Here it's a chance, as Kathy said, 80 out of 240, 0.33, 20 out of 60. So in both cases, the ratio is the same, the odds ratio. But when you have an association, that is, the ratio is no longer 1. It could be bigger than 1 or smaller than 1. When that happens, the odds ratio is always different from the relative risk, always. And so you can show by algebra that the relative risk is always closer to 1 than odds ratio. That's what you'll find. This numerical example, it was 1.7 and 2.4. But this is what you will find with any 2 by 2 table. If you put down a 2 by 2 table and you calculate odds ratios and relative risk, the relative risk will always be closer to 1 than the odds ratio. So, but I will show you presently that the odds ratio is really appropriate only for case control studies. It's not appropriate for any other type of study. The 5 types of studies we talked about, it is not appropriate to calculate or report odds ratio for an intervention study or an exposure match study or a complete cohort. It's only appropriate for a case control. And I'm stressing it so much because you can see any number of papers in the medical literature where they report odds ratios when they should be reporting that. So first, to understand why odds ratios are appropriate for case control. Now, the key point to understand is that in a case control study, the number of controls for each case is arbitrary. You could choose 2 controls. Here, for instance, we have 2 controls for each case. But maybe they say this is what I did. Now, say you do a study in a similar problem, and you decide to have 5 controls for each case. So you shouldn't get different results from it. We should both be reporting similar summary statistics for what the increased risk is from the risk factor. So now, say these are the numbers, you get these odds ratio and relative risk. Now, suppose you have 4 controls per case instead of 2. So let's say everything just gets doubled, the controls. The cases remain the same, 70-30. The controls now are doubled. That is, you have twice as many controls, so 170 becomes 340, 30 becomes 60. Now, if you go through the calculation, the odds ratio is unchanged. This is an algebraic fact you can show easily. Odds ratio doesn't change if you simply double or triple or whatever, if you scale one column by a factor. One column, not a row, one column by a factor, which is what happens when you vary the number of controls per case. So odds ratio doesn't change, but the relative risk changes. It goes up when you have more controls per case. And if I have, say, in my entire cohort, let's say there were 400 controls per case. So the 170 becomes 34,000 and 30 becomes 6,000. The odds ratio still doesn't change. Whereas now the relative risk actually becomes equal to the odds ratio. So in a case control study, that means situation where the outcome is rare and you have a certain number of cases, and you could have huge number of controls, and you happen to have just one control per case or two controls per case or whatever. The odds ratio, in fact, is the correct thing to calculate and report, not the relative. This is not the case always. Suppose, for instance, the entire cohort was only was 3,000. This is a complete cohort study, and you have a breakdown like this, and that is, there were 600 people at a high level of the risk factor, 2,400 at the low level, and it was 10% had an adverse outcome without the risk factor, and 20% had an adverse outcome with the risk factor. Right? Just to look at these numbers to start. 240 out of 2,400, 120 out of 600. But this is the complete cohort. It's not a case control study. You started off with 3,000 people, and this is the breakdown. So the relative risk comes out very naturally. 0.1, to go with what Kathy said, that's the 0.1 is the chance of a negative outcome at the low risk factor, and 0.2 is the chance of a negative outcome in a high risk factor. So the relative risk is 0.2 divided by 0.1, 2. So that's obviously the correct thing to do. But if you look at odds ratio, as I said before, it comes out with a bigger number, and that's wrong. This is not the correct summary statistic. The chance of having a negative outcome doesn't become 2.25 times. It's only double. Or say you have an interventional study. So you have 400 people randomized to two groups, 200, 200. Say on placebo, there was a 30% negative outcome, and in the intervention, you had 12% negative outcome. So the risks are 0.3 and 0.12, so the relative risk is 0.4. That means the risk has been reduced to 40% of what it was. Right? Is that clear? Am I going too fast? So, but if you compute the odds ratio, it now becomes about 1/3. So do people see? Because I'm not just trying to bamboozle people here, throwing numbers out. The point is that it doesn't matter what the numbers are. See, if you have a 2x2 table, the odds ratio will always be farther away from 1 than the relative risk. So in this case, instead of 2, you get 2.25. In this case, instead of 0.4, you get 0.32. In both cases, farther away from 1. So the odds ratios should only be calculated, reported for case control. So that's my rant. And I think that one reason a lot of people report odds ratios is that it looks better, because the odds ratio is always farther away from 1 than relative risk. And okay, so I'm done with my rant. Just very quickly, I think people know some of these terms. So sensitivity is also called the true positive rate. So you say, of the people who have the condition present, how often am I detecting it with my factor being present? So it's a true positive divided by the total of false negative and true positive are added. And specificity is is in the control side, or the people who don't have the outcome. So you have the true negative out of the total, and that's the specificity. So true negative divided by true negative plus false. I had trouble when I first came across these words, how to remember specificity, sensitivity. Some resident gave me a mnemonic that they used, which was quite good, but I forgot. Anyway, my mnemonic is that sensitivity has the letter N, and that goes with false negative, and specificity has the letter P and goes with false positive. Even as I'm saying it, it doesn't seem very helpful. But anyway, that's I think specificity looks at false positive, and sensitivity looks at false negative. And you can calculate positive predictive value, which is of the things that are predicted to be positive, what fraction are truly positive. And you can have a negative predictive value and false positive rate, which is sort of related to sensitivity. You have the same denominator, and false negative rate, which relates to sensitivity. So these are standard terms. Isabella reminded me of something. Just to repeat what I said before, if you have a case-controlled study and a rare outcome, it's fine to use odds ratio. Any other situation, you have to use relative. So if your outcome is at all not rare, and you don't have cases and controls where the number of controls is arbitrary, then you have to report relative. So we have 4 types of observational studies where these things that I mentioned might get reported. We don't usually report these for interventional studies. So these get reported for observational studies. So there are 4 types of observational studies. And so one way to be clear about what to report for which type of study, I think I mentioned it at the very beginning. See how the 2x2 table starts getting constructed. In a case control study, you start with the column total, and then you get the numbers in the 2x2. So because the column is what you start with, the vertical calculations are okay. So sensitivity, specificity, false positive, negative rate are fine to report. But you can't report positive predictive value or negative predictive value in a case control study. And of course, you calculate odds ratio, not relative. Now, in an exposure or propensity match study, you start with the horizontal total. How many are exposed, how many are not exposed, and then you put in the numbers in the 2x2. So horizontal calculations are fine. You can calculate positive and negative predictive values and risk. So you report relative risk and not odds ratio. So just as over here, you wouldn't report predictive value, over here, you would not calculate sensitivity. But if you have a complete cohort where you start off with the grand total and you get the 2x2, you can report all of these, all the things that you can calculate here. And of course, relative risk, not odds ratio. Okay. So I think I'm ready to do some calculations. So I would like you to go to our webpage and work these problems. So going back to the first example I gave of a case control study, these were the numbers. There were 412 cases with childhood stroke and 1236 controls for them. Of these 412, 15 had congenital heart disease, and these 7 had congenital heart disease. And of course, you can calculate these by difference, subtract 15 from 412, 7 from 1236. So I would like you to go to this webpage, biomath.net/stat. Since there aren't so many of you, just raise your hand if you are having any trouble at all. And under that, there's a bunch of options for different types of 2x2s to look at, what we call contingency tables. So case control is what we're going to do first. You notice you don't have to put in the 2x2. You put in what the numbers are for the high risk factor level and the total. These numbers, 7, 12, 36, 15, 4, 12. That's all you have to put in. And the web page will fill in, calculate, and show you that. So you put in 7, 15, 12, 36, 4, 12, and click here for results, and you should see this. So, I'm sorry, where it shows you the 2x2 table, and it calculates odds ratios, because that's the appropriate thing to calculate for case control study. Gives you a p-value, and these things, sensitivity, specificity. So, okay, next intervention study that was reported from West Africa. So these were the numbers. There were about 920 in each group, and 68 died in the placebo, and 38 died in the 70. So these are the 4 numbers that you would put in. So what you do is you go back in your browser and pick intervention or exposure matched. And when you go there, you now see what you're prompted for is slightly different. So you put in the total number in each group and how many cases there were. So there were 68 deaths in the placebo group and 38 deaths in the antibiotic. And again, when you click for results, you get the full table and the p-value, and of course, it calculates relative. And also calculates other things that you can report, predicted value. Any questions? So I'm just going to go by unraised hand. And okay. So then we did an exposure match cohort. So 17,000 Swedes with CD, 85,000 matched. So you can see that these numbers, the layout is very similar to the intervention study. That is, you have a total number in each row, and you have how many cases there were in each row. So these are the numbers that you're going to put in. Now you don't have to change page. You can just work on the same page that you did for the intervention study. You don't need to go back. Just change the entries to these numbers. And finally, the propensity matched cohort. I'm not sure I have a thing for that. So I mean, you can do it yourself. It'll be done also on the same page. So the complete cohort study, and remember here they started off with 96,000 kids with older SIDS. Of them, 1929 had an older SID with ASD, and 994 of these kids had. So here, you do have to calculate all the entries, because in a complete cohort study, we want you to put in all these 4 values into that. So we have to subtract the 134 from 994, get 860. 134 from 1929, get 1795. And then subtract all of these from the grand total, and you get this. Is that clear? So now we take these 4 numbers and put them into our web page. But of course, it's not the intervention web page. You have to go back and pick the complete cohort option. So when you pick the complete cohort option, you now have to actually give all the 2x2 table numbers, not total. There's no row total or column total here, just the individual cells. You put in those numbers, and then of course it shows you the numbers again, and it gives you the risk or rate in the two rows and the rest. Not different from intervention study. it's just that the entry looks different, but also you can calculate more things here, which the web page does, like sensitivity, specificity, true positive, true negative rates, and the predictive value. I think I'm pretty much done with 2x2. Any questions at all? You have the odds in at each level of the risk factor, and you have an odds ratio, and for a rare outcome like here, this is you're talking about childhood stroke. The odds ratio, you can interpret as a relative risk, and so this says basically that if a child with congenital heart disease has more than 6 times the risk of having a childhood stroke, that's what that odds ratio is. Again, in a rare outcome case control study, you can interpret the odds ratio as relative risk, as we saw in the numerical example I worked through, that the odds ratio does approximate relative risk for in that situation. So you could look at this and say a child with congenital heart disease has 6.6 times the risk of having a stroke in child. So that's how it would be read. Whereas in an intervention study, maybe I neglected to do this, and so here the risk of dying in the placebo group was 7.4%. The risk of dying in the antibiotic group was 4.1%. So the relative risk is 0.56. That is, the risk of dying has been reduced from 7.4 to 4.1%, or it is now 56% of what it. That is, this is 56% of this. And or if you want to think of it differently, the risk has been reduced by 44%. Subtract 56 from 100. That's how you would understand relative risk, and of course significant p-value. And whereas in the celiac disease situation, so the risk of having that whatever PHPT or whatever this parathyroidism was 0.2% in the controls and 0.4% in the celiac disease. So that means the celiac disease sort of doubles the risk of having this hyperparathyroidism. So that's the interpretation of the relative risk. So finally, in a complete cohort, we're talking about kids with older SIBs. So now, when the older SIB did not have ASD, the chance of the child having ASD was 0.9%. But if the older child had ASD, then the probability of this child having ASD was 6.9%. So 0.9% became 6.9% if there was an older SIB with ASD. So the relative risk is like 7.5 times. So that means a child who has an older SIB with ASD has 7.5 times the chance of having ASD themselves. So that's the interpretation of the relative. I mean, obviously, I should have said these things before, and I hope this is what the person is looking for. I want to just show a couple of shortcuts as a way to start working in Excel. Now, our web page is fine. It will give you analyze 2x2s and give you, but it doesn't calculate the numbers for you, right? Whatever numbers go into the cells, you have to calculate from your data. So you might have a spreadsheet where you have all these different characteristics recorded. Now you have to add them up. Now, there are various ways to do it. The way I used to do it was I would just sort the data in Excel and then count the rows. I would say, okay, this group starts in this row and ends in this row. So there are so many of those. So that's certainly one way to do that. So I just want to show you another way, which might be of some interest. So this is the data file that we're going to be working with. And we're going to do something that's really not very serious first. So the very first tab that marks propensity, if we ever have time at the end of the 6 weeks, I may, we may analyze those data. But for now, I just want to illustrate these shortcuts by work. I have made up data here on 400 ICU outcomes. Now, so there are, this is sort of an attempt to simulate this example that I had, propensity match thing of freestanding, not freestanding. So here I call them small and big hospitals, and you look at the outcome, alive or dead. So say that's what we want to analyze. Now, so I want to know how many kids there would be in each of the 4 cells, right? If I want to do an association between outcome and size of the hospital, I need to know how many are in each of the cells. So this is how we're going to do this. So you can type this, or you can just copy this from the PDF and paste it into your Excel. So whichever works for you. So I want you to type into L3, this is this table that we want to fill up. And so I want to know, first of all, how many kids were there total in the small hospital. So the way you do that is you say, count the number of cells where in this range, in this column, F2 to F401, there are 400 made up numbers there. So in that range 2 to 401, how many of these cells are small? So that's what this is saying. This is saying count, not just count all the cells, but count if the cell equals small. So you do that, and you should get 200 there. When you hit enter, after you copy paste this or whatever you do, when you hit enter, you should be 200. And next, we want to know how many of these were both small and dead. That is, how many kids died in the small hospital. And the way you do that is with an even longer countif. So you say countif, I want the cell to be small and the corresponding H column outcome cell to be dead. So this is not actually just counting how many are small and how many are dead. It's actually counting how many rows have small in column F and dead in column H. So that's what this count is. So this is what you should see. You should see 200 here and 28 here. And then finally, you type equals a simple formula. You can just type L3 minus K3. That is, the total minus dead would be the number of kids who lived. Interested in copying these formulas to the next row so that I can also do it for the big hospital, not have to retype everything. Still have to edit. So the way you copy multiple cells in Excel or single cell is you highlight J3 to L3, okay? And then you move your cursor to the lower right, and that little black square will turn into a plus sign. And when it is in the plus sign state, if you drag it down, it will copy that row to as many rows as you want. Now, we do need to edit a little bit because in this row, we want things to be big. So we need to change those two cells. Wherever small occurs, you need to change it to big. So it's very easy to do. You just click on a cell and then go up and click inside the formula and then edit the small to be big in both cells. And once you've done that for the two cells, this is what you should see. Just a couple of comments that I want to make here, and that is so one thing to note is that I asked you to edit these two cells in the big row, dead and total. I didn't ask you to edit the alive entry. That got calculated automatically, recalculated automatically. That is, here it was 172. When this 28 became 46, this automatically became 154. How did that happen? So that happened because when you copy a formula, Excel uses some logic to decide whether to change references or not. So here, it was the formula that you typed was L3 minus K3. So when you copy that formula down, Excel changes it to L4 minus K4. It makes a sort of a reasonable assumption that that you want to now to calculate on this row as opposed to the previous. You're calculating in the third row, now it's calculating, making the same calculation in the fourth. And
I was just wondering if you could go over what the countifs function is.
So this is the formula here, right? So it's a sufficiently messy formula. So what this formula is saying is, it's saying count how many rows have this property. That is, the property being the F column should say big and the H column should say dead. That's what the countif does. That is, it counts how many cells in the range you gave. See, there are 400 cells in this range, F2 to F401. So it's not going to give you 400. It's saying, of those 400, how many are big? And simultaneously, in that same row, anytime there is a big, is there a dead in column H? And I'm assuming that you have your data in Excel where typically each row is a different subject and you're working. And so I think I have one more comment about these formulas and these funny dollar signs. And what the dollar signs do, that when you copy those cells, the dollar sign says don't change that. Whereas here, L3 minus K3 became L4 minus K4. For the dead and the total, F2 to F401 or H2 to H401 didn't change. they remain as they are. And that is accomplished by putting these dollar signs in front. So the dollar signs say, don't change the F or the 2 or the F or the 401, etc. when you copy this. So that's the purpose of the dollar sign. I should say, I didn't have to put a dollar sign in front of the F and the H. I needed it only for the 2 and 401 because I'm copying down. I'm not going across. But maybe safer just to do it like. So if there is no dollar sign, Excel changes column letters and row numbers in a logical fashion. So when you go down, L3 minus K3 becomes L4 minus K4. If you went right, then L would become M or and so on. So I'm done with the shortcut. So is there any question about the about that? Okay, so I'm going to go on now, and so we're not going to be doing this anytime soon, but I just want to give you, a picture of where we're going to go ultimately. So you have a 2x2 here. That's what we did, I hope, exhaustively. So when we start with R, we will do contingency tables in R again. Just, you can do somewhat more elaborate tables there. And you also don't have to worry about adding up the cells and so on. R will do that for you. And then we will extend. So there are at least two important ways you can extend a 2x2 analysis. One is, what if you have more than one factor? You have your outcome, but maybe you want to look at more than one factor at a time. So if that happens, we're going to learn to do logistic regression. That's what logistic regression is all about. But looking at a categorical outcome with more than one risk factor, more than one predictor. The other possibility, which I don't want to go into details here, just to say, what if the outcome is not just yes, no, but rather when something happens? So what we call time to caseness. So what if we had time to caseness as the outcome? Then you would do Kaplan-Meier. And and then finally, as far as my course is concerned, you could have both of these. You could have a time to caseness as the outcome, and you could have multiple predictors or risk factors. So then you would need to do Cox proportional. So that's so this is what we will do, towards the end of the course. And once you go beyond 2x2, for any of these, you need packages. You can't do it in Excel. So I want to digress a bit before we start Excel to talk about null hypothesis. I think people have come across the term null hypothesis. And this is what we typically, state a null hypothesis, and then we say our data reject that null hypothesis. And so then we conclude that, yes, this risk factor is significant, or that this treatment really does something, and so on. So a question that I had when I learned statistics that I'm unclear about is, why do you need to do that? Why do you need to state a null hypothesis that you don't believe in? You actually want to show that it's wrong. And why not just state that I think this treatment is better? I think the groups are different. And then prove it with your data. Why do we need to start by assuming that there is no difference and then reject it? So, this is a typical null hypothesis. and this would be, I'd say, an alternative hypothesis to start. So I don't know, would anybody like to speculate, what the value of the null hypothesis? Because to be frank, it was not at all obvious to me for a very long time why you needed the null.
In our stats courses, we were always taught to, or at least I was in like undergrad, that we should be doing treatment and placebo are no different. And I never questioned why. So I think.
Yeah, no, it used to bother me, why do I have to start with the null hypothesis that I don't believe in?
It's easier to disprove.
Okay, go on.
That's as far as my knowledge goes. It's been a while.
Right. No, I think is the essence, Zach. I think the essence is it turns out it is easier to disprove something and then accept what you want to accept in the first place, as opposed to proving what you think is true. And okay. So this is what I want to sort of go through here. And so anyway, I show cartoons occasionally by this cartoonist. I don't know if people know him, Randall Monroe. He has a website, XKCD, and you can have a lot of fun at that website. He does a lot of science, math-oriented cartoons. So you can't imagine, it's hard to imagine some random person deciding to do a cartoon about the null hypothesis. So that's the kind of person he is. So this is so I want to illustrate the point by using the results of a study that I collaborated in, and so I think people in pediatrics would know Melissa Stockwell. She's very, very interested in using technology to improve healthcare delivery, like on-time vaccinations and things like that. So this particular project she undertook to see whether Columbia's decision back in 2009 or so to sync their data with the city health department with respect to immunization status, whether that improved immunization status generally for our patients. So the concern before that was that parent comes in with a child and the kid is due for a vaccine, and then the parent says, "Oh no, we went to a public health thing and she got a shot there." And the information may be a little off, or may not have been a shot for this particular vaccine, and so there would be some uncertainty, and so the syncing basically got rid of that. So it may seem very obvious, but it takes some effort. So this publication was to say, well, other places should consider doing that. It's a very useful thing. So what they did was a 6-month period before the syncing started, about 6,500 kids, and 6 months post syncing, another 6,000 kids. So the up-to-date status, the kids being up to date, increased from 75% to 82%. So that's what the Stockwell's report showed. Okay. So just I want to round numbers, and you may want to go along, do this on your web page while I'm doing this. So this is the outcome. So you could say work in the complete cohort, I think. That might be the easiest way. If you work on the complete cohort and you put in these numbers, 1,600 and 5,000 for the preceding year and 1,400 and 5,200 for the next year, the P is less than 301 under the null hypothesis of no change in utilization. So what is the answer here? Do we reject the null? Anyone want to help me out? Do we reject the null, accept improvement?
So in this case, it looks like we can reject the null because the p-value is so significant.
Right. Okay, great. So stay with me, Dan. So suppose Columbia were a much smaller place than it is now, and the same study was done. And let's say all the numbers were 1/10. So you can do this on your web page. So just change the numbers to 160, 500, 140, 520. So if you do that, you're going to get 0.21 under the null hypothesis. So what do you say, Dan, with that?
I was just saying that I've always been told that we don't technically accept the null, we just don't reject the null.
Excellent, excellent. Yeah. So we can't accept the null, and we can't reject improvement. And I think that Dan said it correctly. We fail to reject the null. That's all we can do with this 0.2. Okay. So I'm going to come back to this in a minute. Yet another little digression, which may not at all be helpful. I thought that at one point it did help me, but I'll mention it anyway. I don't know if anyone came across contrapositive in their undergraduate days in logic or philosophy or anything. So contrapositive basically is that if A implies B, then if B is false, then A is also false. You can conclude that. But if B is true, you don't know whether A is true or false, right? If you start with A and that it always implies B, then by looking at B, you can actually say something about A if B is false. So it's similar to what is happening with the null hypothesis. The null hypothesis leads to a certain probability of what you observe. If that probability is very small, then you can reject the null hypothesis. But if that probability is not small, then you can't actually say whether the null hypothesis is true or false. So I like to give an example, like if I actually do a good job, all of you will become proficient in statistics. So I had a very smart student last year, Atene. So if Atene does stats poorly, you can conclude that I did a shitty job. But if he does stats well, you can't actually conclude anything about my teaching ability because she could have been good independent of my teaching. So that's, again, another, I don't know if this helps at all. So I think it's the same sort of thing that in a certain situation, you can infer something about the starting point. And there's another great cartoon from XKCD. I may come back to it later when we talk about correlation. So this is something, I think I even talked to the residents. Did I? No, I guess not. So it's a common thing. It's sort of drilled into people that correlation doesn't imply causation. So this person says, I used to think correlation implied causation. I took a stats class. Now I don't. So the other person says, sounds like the class helped. And this person says, well, maybe, right? So maybe the class helped the person to learn that correlation doesn't imply causation. But maybe the person came to that understanding on their own. Nothing to do with the class at all. But I do like to add one thing. I may show a video next week, a very short video on that point. Correlation doesn't imply causation, but it demands an explanation, in my view. You can't just reject correlation by saying they don't imply causation. You need to be able to explain why the correlation is there. Okay, so back to. So we already looked at these two situations. Okay. Now, with hypothesis of improvement, though, this was the alternative. Going back to Zach's comment, this was a thing where we could disprove the starting point, null hypothesis, or fail to disprove. But with the hypothesis of improvement, if you say that up-to-date status improved with the thinking, both results are consistent with that, right? Because the numbers are the same in terms of proportion. So they both show some 75 to 80% on up-to-date status. So both results are consistent. So the improvement hypothesis is not useful as a starting point. And I think this is what Zach was saying, that it's harder to prove something than to disprove something in some situations. So along with that, I want to say a little bit about when we might accept the null hypothesis. I know that Zach already said quite correctly that, and Dan also said, we failed to reject the null. And, but in my view, it is possible to sort of accept the null under some situations. And this happens a lot, all the time, and it's good to be clear about when we might do it. So the idea is you first decide on, in this case, for instance, our up-to-date status. You have to decide what's the smallest clinically meaningful improvement. I mean, that's a clinical judgment. It's not a statistical question. So Melissa Stockwell would have to decide what would be the smallest clinically meaningful improvement. Let's say she says it's 4%. That is, the up-to-date status should increase by at least 4% to warrant all the additional work that is required. And so the way to do that is to look at the confidence interval. Okay, so you remember we looked at this? No. So why don't you put these numbers in? So I've changed the numbers to look for a smaller improvement. So I said the up-to-date status increased from 500 to 505, a very small improvement. Now the relative risk or rate ratio is 1.01 because it basically went up by 1%, right? From 500, it went up to 505. It went up by 1%. Now the confidence interval, I think your web page should show, is 0.95 to 1.07. So the problem is that the p-value is very close to 1. But we can't accept the null. We cannot, because this confidence interval includes the 4% improvement, right? The smallest clinically meaningful improvement is 4%, and that is included in the 0.95 to 1.0. So, but what if you had 10 times these numbers? That is 5,000 went to 50-50. The same improvement, RR 1.01, but now the confidence interval is 99 to 1.03. Now, the p-value is actually better. It's 0.32 now. But we can sort of accept the null hypothesis because the confidence interval doesn't include 1.04. It doesn't include a 4% improvement. Of course, it is crucial for this conclusion that you state what the smallest meaningful improvement would be. And basically what you're doing here is you're looking at the confidence interval on what you got in your data. And you say, well, the confidence interval doesn't include what is of interest. And so I'm willing to accept the null.
Sorry, I have a question as well.
Go ahead.
Is 4% arbitrary? Did we choose that, or is that an actual standard?
No, it's arbitrary.
Okay.
Completely arbitrary. So you could say synchronizing between our hospital records and the city health department is so trivial. Even a 1% improvement is significant, right? Or you could say in a different situation, it takes a lot of effort to achieve this the synchronizing or whatever we were trying to do, and so there has to be some clear benefit to doing it, and that 4% would constitute a clear benefit.
Got it. Thank you.
If you can say what the smallest difference that is significant, not statistically, but practically meaningful, clinically meaningful, etc., then it is possible to design a study and so on, or interpret a study and sort of accept the null hypothesis. And I do think that's important because you want to be able to say some treatment doesn't work. So how do you show? How do you show that a treatment is ineffective? Because the numbers are never going to be exactly the same in the two groups. But even if they are exactly the same, the treatment may actually be better. You just happen not to find it. So you have to look at the confidence interval. And so you do have to have some idea. I mean, this may not always be articulated, but I think it's important to have that. Right. So I think I'm done with the null hypothesis part. So I'll talk about p-values for a bit. So it's the probability that the observed data arose purely by chance. I think people know that. And that means no group difference, no treatment effect, no correlation. And what does less than 0.05 mean? It means the probability arose by chance is small, in some. So if we conclude that there is probable group difference, treatment effect, correlation, etc. So why do we use 0.05? It's arbitrary. And so I think, I'm sorry, folks, I want to digress for a minute here. So give me 1 minute while I find something. A little bit from a NOVA episode on PBS, which talked about probabilities and p-values, I think.
In fact, the scientific method demands a hypothesis which leads to a prediction of results from a carefully designed experiment that will test its claim. Surprisingly, it wasn't until the 1920s and 30s that a British scientist, Ronald A. Fisher, set out guidelines for designing experiments, using statistics and probability as a way of judging results. As an example, he told the story of a lady who claimed to taste the difference between milk poured into her tea and tea poured into her milk. Fisher considered ways to test that. What if he presented her with just 1 cup to identify?
If she got it right one time, you'd probably, well, yeah, but she had a 50-50 chance just by guessing of getting it right. So you'd be pretty unconvinced that she has a skill.
Fisher proposed that a reasonable test of her ability would be 8 cups, 4 with milk into tea, 4 with tea into milk, each presented randomly. The lady then had to separate them back into the 2 groups. Why 8? Because that produced 70 possible combinations of the cups, but only 1 with them separated correctly. If she got it right, that wouldn't prove she had a special ability. But Fisher could conclude, if she was just guessing, it was an extremely unlikely result, a probability of just 1.4%. Thanks mainly to Fisher, that idea became enshrined in experimental science as the p-value, p for probability. If you assume your results were just due to chance, that what you were testing had no effect, what's the probability you would see those results or something even more rare?
If you assume that there's a process that is completely random and you find that it's pretty unlikely to get your data, then you might be suspicious that something is happening. You might conclude, in fact, that it's not a random process, that this is interesting to look at what else might be going on, and it passes some kind of sniff test.
Fisher also suggested a benchmark. Only experimental results where the p-value was under 0.05, a probability of less than 5%, were worth a second look. In other words, if you assume your results were just due to chance, you'd see them less than 1 time out of 20. Not very likely. He called those results statistically significant.
Statistically significant. Now, this is a terrible word. It could be quite insignificant. You could be detecting a very, very, very small effect, but it would be called, in the mathematical lingo, significant.
So as is implied in that NOVA episode as well, 0.05 is arbitrary. There is nothing, intrinsically whatever about 0.05. And it's the probability of false significance. And or people say incorrect rejection of the null hypothesis, also called type 1 error, etc. So as was implied in the video, if you do one test and it comes out that way, you can say, okay, I'm rejecting the null hypothesis. But what if you do more than one test? How do you deal with that situation? Any thoughts? This happens a lot. When we do a study, we don't just ask one question and we test a bunch of things. And so should we be worried? Any thoughts? None? Because you can imagine there is a problem, because the probability of one of those things just having a p-value less than 0.05, you can say, that's very meaningful. But what if I look at 10 things and one of them happens to be less than 0.05? Is that still meaningful? And that's the problem. So I like to give an example that if I take a coin and I toss it 6 times, and all 6 come out to be heads, or all 6 turn out to be tails, that is statistically significant, because it turns out the probability of that happening is 1 in 32. So 1 in 32 is less than 1 in 20, and so you can say less than 0.05. But what if I take my coin and I toss 6 times and I don't get all 6 the same? And I say, wait, let me do it again. And I do it again, and I still don't get it. So I keep doing it. Maybe after 5 times or something, I do get 1 6 toss experiment thing where they all are heads or tails. So I can't conclude the same thing at that point as I would have if my very first 6 toss had ended up all 6 the same. That particular 6 toss, of course, is there. All 6 heads or all 6 tails. But it wasn't in isolation. it has to be viewed in the context of my other tests that were done. So there are approaches for this. There is a classic Bonferroni approach, which is to say, well, you just have to have a smaller p-value if you're going to be looking at multiple things. So I think people see GWAS papers, genome weight association studies, where they're looking at hundreds of thousands of tests or millions of tests. So they don't consider anything significant unless the p-value is really, really small, like less than 10 to the minus 10 or something. So that is, the way you have to deal with it. Anyway, but I don't deal with this problem at all. And, it's something you need to be aware of. But I'll leave it there. So I have yet another cartoon from Monroe. So about p-value. So the way things get reported. And I know because some of my colleagues do the same thing. So the p-value is like 0.03, 0.01, very significant. And if it is somewhere close to 0.05, just say it's significant. And if it is 0.05, not that it has happened with my colleagues, people might say, let's redo the calculation. And so this is where the spin comes. You say on the edge of significance. It's significant at 0.1. So my colleagues might use terms like trending to significance, etc. So you modify it. You don't want to give up that it is significant, but you modify it. So, and the other thing that gets done is you look at subgroups. Overall, it's not significant, but if I look at just this one subgroup, I do find it. So all of these, the subgroup analysis again has the same problem as asking multiple questions. It's the same concern. So okay, so we are on to my second topic, what you can do in Excel. And we're going to learn to do basic data manipulation. We're going to look at correlation coefficients, scatter plot, and t-test. So, and really, in terms of data manipulation, what I have to teach is nothing new. For instance, the countifs that I talked about before, I learned that by Googling. That's how I learned. So, okay, so we're still going to work in the first tab, the propensity tab. At the very top of that thing, all the way on the left, I have a few numbers. These numbers. I have some triglyceride values ranging from 50 to 130. And so we want to calculate the median, 25th percentile, and so on. So these are the data, and we're going to start making some calculations by typing formulas. So I would first like you to type a formula for the median. It's pretty straightforward. By the way, I didn't mention it before. In Excel, if you start typing with an equal sign, Excel assumes that you have a formula of some kind. And so you type equals median B1 to B9. That's it. And that will give you the median of these 9 values. So you should get 90 in your spreadsheet. And then the way you get 25th and 75th percentile is just, there is a function called quartile. And if you ask for the first quartile, you'll get the 25th. And if you ask for the third quartile, you'll get the 70th. I should have my chat open. This is what you should get. And finally, mean and standard deviation is pretty straightforward. You say average. Now the function name is not mean, but average. You do it the same way. And then you do standard deviation. You want to be nice, and you should get all these numbers. nice thing in Excel is that once you have your formulas in, if your data change in some way, you generally don't have to redo the formula. So like if you change some number, Excel will automatically change all cells that are affected by that number. So to take a simple example, if you take these things, the data that you have, the 9 subjects, just delete the last subject. Just delete it, and you will see immediately all these numbers change. Because Excel sees that this value is no longer there. 130 is no longer there. So the median goes from 90 to 85, mean goes from 90 to 85, and so on. The standard deviation changes. So again, nothing very profound here. Some of you it may be very obvious that you have a lot of experience with, but just something you need to know. So I want to spend a few minutes over what the medians and the quartiles are. So these were the numbers that came up for the median and the 25th and 75th percentile. So I hope it's clear why this is the median, right? Does anyone want to say why is 90 the median of the data? No one wants to say.
It's directly in the middle.
That's good. That's good. So Dan, do you want to try saying why is 70 the 25th percentile?
It's roughly at the third rate. So like out of 9, it's third. So that's the cutoff.
Right. Another way to see it, Dan, is to see how many are below and how many are above that value. So you have 2 below and 6 above. So that ought to be the 25th percentile, right? Because 25th percentile means you have 25% below and 75% above, or 3-to-1 split. And so you have a 3-to-1 split here at 70, 2 below and 6 above. And the same thing happens at 110. You have 2 above and 6 below. Now, it gets a little bit trickier when there are only 8 subjects. So Dan, what should be the median now? What should the median be here?
So you would take the 2 that are directly in the middle, so 4 and 5, I believe, and you would take the average of those, so it would be 85.
Right. So Dan, you're quite correct. That you want to be between 80 and 90, and it's taken to be 85. So how would you calculate the 25th percentile now?
I think it's the same logic.
Okay. So what would it be, you think?
So it would be the average of 2 and 3.
Right. So it should be 65, right?
Yeah.
So Dan, you and I are alike because I had the same thought as well. But it turns out that's not what Excel does. It actually moves it closer to the third value than to the second value. And you can sort of imagine some rationale for it. So that is, instead of going halfway, it goes 3/4 of the way from 60 to 70 and takes it to be 67.5. And likewise, the 75th percentile, instead of being halfway between 100 and 110, it's 1/4 of the way from 100. And so it's 102.5. So, I mean, these things are, maybe arbitrary, but this is what the Excel and stats packages do. just something to be vaguely aware of. But this is what you get. Okay, so much for median and the quartile. And so now the distribution is skewed. So I made up some numbers which started at the same place with the same median, but the upper values are spread out more. Instead of going up to 130, they go up to 190. So, so what happens when a distribution is skewed? What you have is the median minus the 25th, and the 75th minus the median are no longer close. Whereas here, they were both 20. Here, the median minus the 25th is 28, and the 75th minus the median is 44. So when the distribution is skewed and you have more values, larger values are spread out more, you're going to have a bigger spacing from the median to 75th than from the 25th to the median. So I'm mentioning this because this is something that you should think of doing with your own data, almost, like routine. Even before you start doing any fancy statistics and so on, once you have your data in Excel, look at the quartiles and the median. Does the median seem to be somewhat midway between the 25th and 75th percentile? If it is not, maybe you don't have a normal distribution because your distribution is skewed. So it's a very simple normality test, asking whether the distribution is symmetric or not. How does another simple test to do for normality is, are the mean and median close to each other? So what you will find is that when the distribution is symmetric, the mean and median would be the same. But when it is skewed, typically the mean would be larger than the mean. So here the mean is 103 above the mean. So this is another simple normality test. Look at the median where it sits between the 25th and 75th, and look at the mean. See whether it is close to the median or not. Again, we're not being very formal here. When we do R, we will learn, that there are simple normality tests that can be done very easily in R. We have functions that will do them automatically. But while you're collecting data and assembling the data in Excel, these are things that you should do. And finally, in terms of summary stats, standard deviation. So standard deviation is a measure of the average distance of the data point from the mean. So if you take these values, if you subtract 90 from all the values, you will get minus 40, minus 30, and so on up to plus 40. So does it make sense just to average these numbers? And if not, why not? Any thoughts?
No, because they would average to 0 because some are negative.
Exactly. Dan is quite correct. In fact, that's the definition of the mean. The definition of the mean is that you choose a point so that all these deviations add up to 0. That's what it will amount to. I know we take a numerical average, but if you do the algebra, you will find that, in fact, if you do all the subtraction, they will add up to 0. So what we do instead is we square the values. We square all the values, but notice now the minus 40 and the plus 40 both turn into 1600. So they're not going to cancel each other, and they're going to add. So you average these, and you take the square root, and you get the standard deviation. So this is the formula. So anything odd about this formula? I've added up all the squares, average, and taken the square root. So anything weird here?
Well, you divide by 8 instead of 9 because you're always going to have the actual average in there as well.
Right. So why am I dividing by 8 and not by 9? In a sense, this is not a great example. Sarah is correct in observing that this is the key difference, but it's not because one of the values is 0. That shouldn't affect the average. So there is no simple theoretical explanation for this. When I learned stats, we learned to calculate bias, and that you can show theoretically that if you do lots and lots of these, if you use 9, you will get a biased value for the standard deviation, not the true standard deviation. But the way I like to remember and I like to tell people is that the way I say it to people is, suppose instead of 9 values, I have only 2 values, just 2 values. Let's say I just have 80 and 90. Can I calculate a mean? Of 80 and 90? Sarah?
Yes.
You can. Now, can I also calculate a standard deviation? I mean, regardless of what the formula is.
Sure.
You can calculate standard deviation also, right? You can take 85 and subtract from 80 and 90 and square and so on, right? You okay with that? Okay. But what if now I only have one value? I just have one value, 70, one subject. Now, can I say what the average is?
Yeah.
And the average is 70, right?
Yes.
Now, can I say what the standard deviation is? This is where it gets a little tricky. So the 70 is not the whole population. The 70 is a sample from a population. And I want to know, can I estimate the standard deviation? And so the answer is, I cannot estimate the standard deviation, right? Because if my sample has only one subject, I have absolutely no idea what the standard deviation is, because I don't have any idea of the variability of the data.
Could you say the same about the average?
No, because the 70 is the best estimate I have of the average. I mean, as the sample size increases, your estimate of the average gets better, right? But for, here I have 9 values. If I had 100 people from my population, my average would be even better, right? It would be even closer to the true mean. But even one value does have information about the true mean, because given a sample of 1, I'm more likely to have a value closer to the mean than very far from the mean, right? Because it's a normal distribution.
Right. So you're saying that with standard deviation, you don't have that because you only have one, so you don't know how they're different.
That's right. I have absolutely no information about the variability of the data when I just have one value. So what I tell students is, if you subtract 1 in the formula for the standard deviation, what will happen if I only have one value is that I will end up with the square root of 0, right? Because the 70 is the mean estimate. So I subtract that, I get 0, square it is 0, and I divide by n minus 1, that is 0. So I'll have 0 divided by 0, which cannot be calculated. So by having n minus 1, I make sure I don't end up reporting standard deviation of 0, but I only have one value, because the formula will say cannot be calculated. I don't know if that helps or not. That is, one way I explain. Any other way of explaining would require a fair amount of algebra and calculus. Okay, so we'll leave standard deviation there. I have some formulas, algebra here, and there's no need. You can look at the formulas. This is what the standard deviation is, n minus 1, and so I'll say a little bit about normal distribution, and then we'll see if we can do some more data manipulation. Maybe we can't today. We'll see. So the thing about normal distribution, the reasons why it is so popular is that it does approximate reality in many situations. And it does so with a very minimal formula. There are only 2 parameters in the equation. So you can have these 4 different distributions. There's very broad distribution, a very narrow distribution, distributions that are separated. They are all described by the same normal distribution, with just varying just 2 parameters. And the main thing for me to keep in mind is that if you go out 1 standard deviation from the mean, you're going to cover 2/3 of the population. 2/3 of the population will be within 1 standard deviation. And if you go out 2 standard deviations on either side of the mean, you're going to include 95% of the population. And if you go 3 standard deviations, you pretty much include everybody, 99.7%. One simple thing to do in terms of a normality test is to ask how many outliers you have, how many points you have that are more than 2 standard deviations away. So if you have quite a few, then maybe you don't have a normal distribution. And you can even get rid of one of the parameters by looking at what they call standardized normal distribution, which is a distribution with just 0 mean and standard deviation of 1. So these are the numbers that I try to keep in mind. Often, when you see a lab report and they have a normal range, the normal range is often plus minus 2 standard deviation. And so, for instance, if the sodium normal range is 136 to 144, what's the standard deviation?
Is it 4?
No.
Oh, 2, right? Plus minus 2
Yeah,
deviation.
that's so 136 to 144. The mean is 140. So you're right. It goes 4 above, 4 below. And then given a sodium value, you can calculate a z-score. So if you have 142, it is 2 above, and a z-score of plus 1. If it is 130, and my mother at one point had severe hyponatremia, so she went down actually even to 120, I think. We thought she was going to die. And untreated, 130 is 10 below and a -5 z-score. So you go on a Vaptan, it brings your sodium up. Now it's 3 below and it's z-score of -1.5. So the z-score is a simple way to describe where some observation is in relation to the mean, because it's standardized. That you can interpret the z-score +1 or -5 without knowing what the standard deviation is or what the mean is. This is simply saying you're 5 standard deviations below the mean. So a lot of testing with statistical analysis, you end up calculating something like a z-score. Like a t-test, you compute a t-statistic, which is not unlike a z-score. And you ask, is this close to 0 or not? And so just to be clear, the statistical tests I'm going to be teaching, you're learning, and so on. Many of them assume normality. And if the data are not normal, these standard tests may not be appropriate. And we'll talk about alternatives when we do R. And so this just to keep in mind, a normal distribution, the mean and the median and the mode are all the same. And most of the time in biological data, asymmetry is the main reason for non-normality. And so if it is unimodal but asymmetric, you can consider a transformation. So for instance, like in our data, in our work, we routinely take log triglycerides. We find that triglyceride levels, they go up, but they're skewed. So, and some people have very high triglyceride levels, but nobody has negative triglyceride levels. So the distribution is skewed. So we find that if we take log triglycerides, we can analyze that like a normal variable. So this is an example. I have 3 examples here of non-normal distribution, and I might invite you to speak up. So this is a distribution of annual household income in the US about 10 years ago. And so you can see clearly the distribution is skewed. You should ignore these 2 bars because some people make so much money, they had to collapse the distribution there. So what you see here is that the mean actually is over 100,000. The median is about 50,000, and the mode is actually around 20,000. So this is the mode, this is the median, and the mean is around. So this is clearly not a normal distribution. And in fact, if you go to various government sources, census and so on, they won't report means and standard deviations at all. Everything is reported in terms of percentile. So if you needed to do regression, etc., it may be that you can work with log income. I haven't tried. So this is another distribution where they did a survey of law school graduates about 15 years ago, and this is the distribution they got. There was some percentage had gone to fancy law schools and gotten well-paying corporate jobs, and a large number of people didn't have that. So you have what is called the bimodal distribution. So can this distribution be made normal? So this cannot be made normal because it has 2 modes. Regardless of what transformation you do, you're not going to get rid of the 2 modes. So you just can't treat this as a normal variable. And this is another distribution. You might say it's silly. If somebody actually monitored how long people stay on a web page, and they had, lots and lots of data, and they summarized it. So at each time spent on the web page, they said what fraction of the total number of visits people spent that much time. So it turns out the most common time that people spend on a web page is 0. They go to a web page and leave right away. And So it turns out this cannot be made normal because the peak is at 0. So there is no transformation that you can do that will make it a symmetric normal distribution because the peak is at 0. So these are two examples of distributions that cannot be normalized. So we'll start with that. We'll start with the slide next week. So are there any questions about today before I wind up?